Okay, today we're actually going to learn how to carry out a hypothesis test when we have a proportion. If you remember back to the beginning near the beginning of class when we talked about a normal distribution and we found our height and the mean was no standard deviations and this would be like one standard deviation away from the mean. Let me fix that. So that's about one standard deviation away, and this was 2 standard deviations away, and anything greater than 2 standard deviations or less than 2 standard deviations was considered unusual most of the time, and 95% of our data lies roughly between 2 standard deviations. And we found our z-score and we figured out where we were in the normal curve. And I think that most of us were inside that normal curve. Well, that is what we're going to do tonight. We're going to standardize our scores and we're going to check against our hypothesis and our alpha level whether our score is considered unusual or not. And the way that we're going to do there are a few different ways to carry out a proportion hypothesis test, and the way that we're going to do that tonight is the classical method. And I'll show you how to do another method next class, but for now we're going to learn the classical method. So if I were to find a z-score for a proportion and it were greater than 2 or less than -2, then it would fall in either of these critical errors, and we could say that our data was unusual. So whatever our claim is, it's going to lie in this region, and whatever we find, we're testing it against the claim to see if it's unusual or not, because that's when we can challenge our claim. Now, it's not always going to be 95%. That depends on our alpha value. So let's get started. The notation is, N again is our number of trials. That hasn't changed. X is our number of successes. That hasn't changed. And our P hat is our proportion estimate, and that's the number of successes over the number of trials. And P is our population proportion. That's what we're hoping to find. And we're going to find the z-score, or our test statistic. We're calling it our test statistic because we're testing it against another z-score, our critical value. So our test statistic we're going to call z0. And that will be p hat minus p over our standard error. Okay, so this hopefully will make more sense when we go through an actual example. Our first example is a June 2007 study conducted by SAD revealed that 37% of teens 16 to 17 years of age text while driving. So that's the claim. The claim is that 37% of 16 to 17-year-olds text while they're driving. A 2009 study by Princeton Survey Research found that 272 of 800 randomly selected 16 to 17-year-olds had texted while driving. Based on this study, can we prove that the proportion of teens texting while driving has changed since 2007? And our alpha is 0.05. And remember that when we were doing confidence intervals, 1 minus alpha was our confidence level, and alpha was outside of our confidence interval. So if alpha is 0.05, 1 minus 0.05 is 95. So that's the region here. And depending on our which tail we're looking at, it'll depend on what we do for our z-score. All right, so let's set up our null hypothesis so we can figure that out, and our alternative hypothesis. Our null hypothesis is that p is equal to 0.37. Now, we want to see if we can prove the proportions of teens texting while driving has changed. So if it's not p, and that's just going to be p is equal to 0.37. So that means that we're looking at a two-tailed test. 0.95% of our data is in the middle of a normal curve, and then these two regions together are alpha. So each region in and of itself is alpha divided by 2 because it's half of the alpha. And if you remember from doing confidence intervals, the z that goes with that, z.05 and z of 975, sorry, this is 975, this is 0.025, was negative 1.96 and positive 1.96. Okay, so we're going to find a z-score that goes with our observed value here, and we're going to find out if we're looking to see if our test statistic is less than negative 1.96, because that would put it here, or if it's greater than 1.96, positive 1.96, because that would be in this region. And again, if it's in our tails, it's unusual, because if you think about it, this is the bottom 2.5% of all data in a normal curve, if 37% is our proportion, and then this would be the top 2.5%. So let's calculate what p hat is. So that gives me a value of 34%, or 0.34. All right, and then I can go ahead and I can calculate my test statistic. So that's my test statistic, and that's going to be p hat minus p divided by my standard error, which is going to be 0.37 times q, which is 1 minus 0.37. That gives me 0.63. And then divide that by my sample size, and take the square root of all that. Gives me a z value of negative 1.76. So that is the value that I'm testing, is negative 1.76. And I need to look on this curve and figure out if 1.76 is in my critical region or not. And you can see that 1.76, or negative 1.76, would fall over here. So it is not in the critical region, so we would fail to reject our null hypothesis. We don't ever accept it because we don't know for sure if it's true, but we fail to reject it. And what we would say about that, I'm going to write it up here because I'm out of room on the bottom, is that there is not sufficient evidence that at the alpha equals 0.05 level to suggest that the proportion of teens who text while driving is different than 0.37. Okay. Why don't you try example 2? At least set up the hypothesis test, then check that, and then you can try the next step. Okay, so in December 2001, 38% of adults with children under the age of 18 reported that their family ate dinner together 7 nights a week. In a recent poll, 403 of 1,122 adults with children under the age of 18 reported that their family ate dinner together 7 nights a week. Has the proportion of families eating dinner together decreased? Use alpha equals 0.1. All right. So if we set up our hypothesis, that's going to be, our null hypothesis is that P equals 0.38. That is our claim right here. And then we're challenging that. We're wondering if it is less than 0.38 because we're wondering if it's decreased, which would mean it's less than 38%. All right. So now I want you to find the test statistic and draw the curve. And when you're done, restart the video and check it. Okay, so if you draw the curve, I'll do it over here. Our line's a little bit deeper than that, sorry. Just ignore this line in the middle there. We are looking where the area is 10% down here at the bottom. Up here would be the normal area, or the area we might expect our proportion to be. And our z-score, and we would find that by doing inverse norm of 0.1, that z-score is negative 1.28. Okay? So everything, all the proportions less than that are 10%, and all the proportions greater than that are 90%. All right, so I need to find my proportion estimate, and that's going to be x over n. So that's 403 over 1,122. And that is a proportion of 0.36, which is less than 0.38. Let's see if it's statistically significantly less than 0.38 to warrant rejecting our null hypothesis. So our test statistic is going to be 0.36, because that's our estimate, minus 0.38, that's our claim. divided by the standard error. And that is going to be 0.38 times 0.62 divided by 1,122. When I calculate that, I get negative 1.38. All right, so if I look over here on my curve to see where negative 1.38 is, remember the middle is 0 and the numbers get smaller as I go to the left and larger as I go to the right. 1.38 is less than 1.28, so that's going to be in my critical region. That means that that number is statistically significant. So we reject the null hypothesis. We do conclude that the proportion of families who eat together 7 nights a week has decreased. So we would write that as there is evidence to suggest. We can't say that it's true for sure, but the evidence suggests that the proportion of families who eat dinner together is, we could say, is less than 38% or has decreased to less than 38%, something like that. All right, what I want you to think about before class is some other ways that you might be able to test to see if something is significantly or statistically significant. But that's it for tonight.